Okay, calculus students, this is Mr. Lovelace. This is your class video for Monday, the week of Monday, March 23rd. I want to start by looking at the calendar because there are a few changes right away. So what I want you to notice is, first of all, on your calendar, Friday is a work day. So this needs to change to be a work study day. You'll have a work study assignment. Starting at the beginning of the week today, I've asked you to read section 4.2 in your book. Just focus on these two pages, 259 and 260. This is the video that I want you to watch in addition to the one that I posted earlier this morning about the week overall and some general comments. You really need to watch both videos so you get all the announcements that are relevant to every student. Okay, then Khan Academy lessons. There are just 4 for this week. There's a video, 2 videos, an article with examples, and then a set of exercises. The exercises are accessible from inside the article at the very end. I've also assigned them to you as an actual assignment. So probably it's best if you watch the videos, go through the article, but don't click the exercises from inside the article. Go ahead and go back out into your Khan Academy and go to the exercises directly from that access point so that I make sure I have record of what you've been doing. So that's the Khan Academy, and that will be due because of your work study 2 days this week. We're going to make those due on Sunday, March 29th. So that's a week from yesterday. So that gives you a little more time this week because of your added workload, work study assignment load. So the only thing that will be assigned, just to clarify for this week for grade purposes, will be the exercises that will go in as a homework assignment for this week. So make sure you complete that. Then you will have a Google form assessment, just like this past week, that you'll need to complete that will go in as a quiz grade. I'm probably, watch for another video from me. These are the homework problems out of the book I want you to work on, 1 through 21 odd. I'm going to do a couple of examples here today. And then the rest of this along with these lessons from the Khan Academy, which you'll see still in your Khan Academy, but I moved the due dates to next week. So for this week, your focus is on summation notation, and we'll be doing some examples of that right now. And then there are 4 items in Khan Academy that you need to complete: 2 videos, an article with examples, and then a set of exercises. So that is actually what you need to focus on this week for this class. Okay, so real quickly, to set the stage for why we're looking at this subject, this is back at the beginning of chapter 4. We talk about the main question that we're looking at here in this part of calculus, integral calculus, is to find the area underneath the curve. And so I pointed this diagram out to you last time, that what we're looking at is thinking about using the shapes, in this case a rectangle shape, to approximate the area by changing the size and number of rectangles and letting that number of rectangles increase until we actually obtain the area under the curve. And this is the procedure that we'll be looking at, that are called Riemann sums, which if you're working ahead, you'll be able to see how that actually comes together. But in order to set the stage for that, we need to cover something that we didn't get to in pre-calculus, which is called sigma notation. And sigma notation is just a shorthand in math using this symbol, which is the Greek letter S, or sigma, capitalized, and it notates the sum of things. Okay, and so what you'll notice is the notation is the sigma, the large sigma letter, and then underneath we have what we call the index of summation, the letter I. Typically doesn't have to be, it can be any letter really. So I equals 1 to n. So this is asking us to take terms of a sum, the n terms of a sum, so these are n items or n numbers perhaps, that will be added up, and we abbreviate that by showing this symbol. So the sum of a to the I, a sub I, sorry, from 1 to n. So there are n terms here. The ith terms, odd way to say it, but it's the ith term is that particular term within the sum. So the 3rd term of the sum, or the 5th term of the sum. In this case, the last term of the sum would be the nth term. Okay. So that's just a shorthand symbolism. So here are some examples on page 259 of different kinds of sums. You'll notice that the index can be called I, be called J, be called K. Those are the 3 most typical letters used to describe the sum. And if you, the index of summation. And if you look inside each of these expanded sums, you're going to see where the index shows up. For example, here in this sum right here, this letter C. The thing that's changing as we go from term to term is actually the number being squared. So if we go look back at the sum notation itself, we see that the index J is this number that shows up as the number that is being squared in this sum. Okay, starts at 3 this time and goes to 7. So this would be the specific sum itself. If we look down here at part D and we look inside the terms of this particular sum, we notice is that the thing that's changing is this first number inside parentheses that's being squared. 1 squared, 2 squared, up to n squared. N, however, doesn't change. You'll notice it's common all the way through. And for a specific sum, n is a fixed number. Could be 5, could be 10, could be 12, or so forth, right? But it's a fixed number. So it doesn't change when we go from term to term. It's a common term in this case, it's a common factor in each term of the sum. Okay, so those are some just sort of overall examples. And then really important sort of box to look at on page 260 is this box they call Theorem 4.2. And this is a very common set of results that you're going to want to have access to and just sort of keep visible, available to you as you're working through these problems, which is how can we actually evaluate some particular values of a sum. So here's number 1, the sum of a constant term from 1 to n is just that constant term times n. So think about putting a specific number in there, like 2. If I want to add 2 up, and I want to do it 1 to n, so each time I write out the term of the sum here, it's just going to be the same thing, 2. So if I have 5 2's and I add up 5 2's, that's 2 plus 2 plus 2 plus 2 plus 2, 5 2's. So that is the same as taking 2 times 5, which would be 10. Okay, so for any constant number or term that is constant with respect to the index, it's just going to be however many terms I have times that thing. Okay, if I add up the index itself, so I take 1 to n and I add those up, so 1 plus 2 plus 3 plus 4 plus 5 up to however many terms I have, I can find that result just by taking the number of terms I have, so let's say 10, times the number of terms plus 1 would be 11, and then dividing by 2. And over here in the margin, you're going to see the result illustrated in a famous sort of historical story about the mathematician Carl Gauss. And that's an illustration of how this actual theorem is applied. And then this also works for I squared or I cubed. Okay, so this is a very important piece of information, a set of results that you're going to want to have access to in order to understand what's happening in this section. Okay, this will be also shown in the Khan Academy videos. Okay, so like I did last week, I want to do now is go to the exercise set and work through a couple of exercises. So for section 4.2 for this week, if you look back on that corrected calendar, okay, what I'm asking you to do is just 1 through 21 odd, okay? And so what I'm going to do is work through just a couple of problems here, starting on page 267. I'm going to do problems 4, 10, and 20. And so if you want to follow along, go back to this video as you're working through the homework set to figure out what's going on. Okay, so first of all, we're going to take problem number 4. Okay, this is asking us to take the sum, the given sum, which is indicated by the sigma notation. J is our index of summation. And we're going to go from j equals 3 to j equals 5 with this term. Okay, so the first thing we're going to do is write out what each term looks like as we change the index of summation. So first we would have 1 over 3 for j equals 3. Okay, I'm going to add, and the next term would be 1 over j, where j is 4. And finally, 1 over j, where j is 5. Okay, so we really just have the sum of these 3 fractions, which of course leads to us having to think about how to add fractions. We'll find our common denominator, 3, 4, and 5, would be 60. Okay, and then we change each numerator. And then add numerators. and then check for common factors, which there aren't any. And so our answer would be 47 over 60. Okay, so once again, all we're doing is taking the term as defined, replacing the index wherever it appears in the term with the numbers, and then writing out the sum. So there are 3 terms in this sum indicated by the index values of 3, 4, and 5. And then to evaluate, we just add the fractions. Okay? Number 10, okay, let me display this one more time because it was a lot to write out individually. And number 10 is asking us to use sigma notation to write the sum. So they're giving us the terms of the sum written out, and they're asking us to write it using sigma notation. So instead of starting with the sigma notation like we did here in number 4 and writing out the sum and then evaluating it, here we're going to start with the pieces of the sum and we're going to go backwards and write it in sigma notation. Okay, so what I've written out on my paper is number 10, find what's changing. Okay, because the thing that's changing in each sum is going to be related to your index of notation. Oh, sorry, index of summation. Okay, so if we look at number 10, okay, if we look at number 10, we're going to try to identify what's changing. So every term has a set of brackets. Inside the brackets, every term has a 1 leading and then a subtraction. So that's not what's changing. Then we have in each term, we've got a fraction that's being squared. And if we look at the fractions closely, what we're seeing is the thing that's changing is the numerator of the fraction, starting at 1 and then 2 and then ... just means that pattern continues up until this term of 4 over 4. Okay, so what we notice is changing is the numerator of the fraction inside that's being squared, and that's our index. Okay, the index is what changes each time. So we're going to go back now. We're going to write out what this thing looks like. So the basic term is going to be the same. The same elements are going to be preserved. We have the brackets, we have the 1, we have the subtraction, we have the fraction squared with the denominator 4, and then the thing that's changing is our numerator. So that's our index value. So we're going to write the sum notation. First the sigma. Okay, we're going to pick an index. Let's use I. There, once again, you can call it I or J or K are the 3 most typical ones. Then we're going to write what's common. Okay, what's common is the brackets. What's common is the 1 and the subtraction. What's common is the fraction form and the power of 2. The 4 doesn't change in the denominator. What changes is the numerator. Okay, so as the index changes, the numerator changes. And then we go back and we look, where does it begin? So if you look at problem number 10, the very first numerator is a 1. So that's our first term is determined by the index of summation equal 1. And the last is determined by the index of 4. So this summation of sigma notation, the sum from I equals 1 to 4, this term, where the index is the numerator of this fraction, would be expressed as this. Okay? So in these other problems I've assigned, 7, 9, and 11, that's what you're going to want to do first, is determine, okay, what's changing, and can I determine from what's changing where the index of notation actually is. Okay, some of them will be a little more challenging than others, of course. Okay, and then last, number 20. Okay, number 20, look at the directions, asks you to use the properties of summation to evaluate the sum. You don't have to do the second part using the summation capabilities of a graphing utility. Okay, but we are going to want to use the summation results on the page that I pointed out earlier, which is page number 260, the summation formulas. Okay, and you'll notice in this, right, there are 10 terms in the sum from 1 to 10, and the index appears in 2 places. It appears here on the outside as well as here on the inside. So if we had enough time and inclination, we could write out all 10 terms, right, and add them up. Well, you could do that, and it would take a while, and it wouldn't be the most efficient way since we have these other results. So if you look back on page 260, you're going to see 2 different results that we think might be useful. Okay, we've got this one where the I index is just by itself, and then we got this one, I squared. We also have this one, I cubed. Okay, So as it turns out, in this one, we're going to use all three of those, and probably this one. All right, and that happens a lot in these problems. You end up using more than one of these formulas. Okay, but the first thing you're going to want to do is multiply this out. And when I say multiply it out, I mean inside we've got I times I squared plus 1. So we're going to write that as I cubed plus I. We're just going to use the distributive property and write that as I cubed plus I. And then right above on page 260, you've got this very important thing, right? Which says that if I take the sum of a sum, I can break that up, okay? So if I have these two different indexed terms, I can break them up into two sums as long as I don't change the limits of the sum itself. Okay, so in this case, what I want to do is break this up into pieces like so. Okay, so I'm just taking this sum and I'm breaking it up into these two sums. And now, if you look back on page 260, we have a formula that will tell us the value of this, and we have a formula that will tell us the value of this. All right, so we're going to apply those formulas directly. Okay, so for the first one, the sum of I equals 1 to 10 of I cubed. If you look back at the form, the sum of I equal 1 to n of I cubed is n squared times n plus 1 squared over 4. And in our case, n is 10. So it's going to be 10 squared times 10 plus 1 squared over 4. And then we have the second sum, which is the sum of 1 to 10 of I. And if we look back at our formulas on page 260, that's going to be 10, which is n, times n plus 1, so that's 10 plus 1 over 2. Okay, so this sum is this value, this sum is this value. And now it's just a matter of multiplication and simplification. So 100 times 11 squared is 121 over 4 plus 10 times 11 over 2. Okay, so that would be the first pass. And then we're going to notice there's some things that cancel, right? 4 goes into 100 25 times. 2 goes into 10 5 times. Okay, and now it's just a matter of multiplying out these two terms, okay? So we would take 25 times 121, and we would get 3,025. And we would add that to 55, and we would get 3,080. Okay, so that's problem number 20. All right, so this week we're going to spend time doing that. We're going to spend time learning how to use these sums, and then we'll see next week how we apply that process to actually evaluating the sums of what we call the Riemann sums, which are going to help us find. Ultimately, our goal for this is to use that information and that process to help us answer this question back on page 247, right? How do we actually use those different shapes, in this case, they're rectangles, in order to approximate the area of the underneath the curve. And, you know, spoiler alert, right? The number of rectangles is increasing, and what we're going to eventually do is let that number go to infinity and use the limit process to find the area. Okay, so we're building that up. We're using the building blocks to help us actually develop that. Okay, once again, a fairly long video this week, but it's important for us to have enough time to look at these examples. Make sure you're using the Khan Academy videos to your best use and trying those exercises, and there'll be more to come in terms of follow-up videos as you need them. So send me questions by email, post them on the parking lot. Don't forget about the parking lot. It's a way to send common questions to the whole class as well. Okay, have a good week and check back in Google Classroom for more information.